In this lesson, we'll discuss a certain vector operation for multiplying two vectors together, and it's called the dot product. Now, in statics, it has two important applications. The two ropes that tie the ship to the harbor can be represented by position vectors, like this and this. And we can determine the angle between these vectors using the dot product. And another thing we can do is we can find the projection of one vector onto another, like projecting this vector onto the other one and getting the green result. But before we do these two applications, I first have to define what the dot product is. The dot product, read as A dot B, is simply equal to this formula, the magnitude of A times the magnitude of B times the cosine of the angle theta that's made between the tails of the two vectors. And this angle has to be between 0 and 180 degrees. Now let's use this basic formula and find the dot product between some Cartesian vectors. For example, I dot I. If we follow the formula, we find the answer is the following. The magnitude of I, of course, is 1, so that would be 1 times 1, meaning A times B here, and then the cosine of the angle between the vectors, and of course that's the cosine of 0 degrees. This, of course, is equal to 1 also. Therefore, the product of 1 times 1 times 1 is simply equal to 1. I dot I is 1. How about I dot J? Well, that's simply 1 times 1 times the cosine of 90 degrees. And if you carry this through, of course, we know this to be 0, and therefore our result is 0. I dot J is 0. Now let's carry these ideas a little further. Let's consider finding the dot product between these two Cartesian vectors written in general form. In order to do it, then, we have to take this term and dot it with this one. And of course, that would give us ax, bx, I dot I. And then we take this term and we multiply it by this one. And there we get ax, by, I dot j, and so on. Now let's carry out all the dot products. We found this to be equal to 1. And of course, j dot j would also equal 1, and so would k dot k. And we also know that I dot j, of course, is equal to 0. So this term would actually cancel away. Same thing here, of course, because we know the angle between these two unit vectors is 90 degrees. And following the same idea, this would go away, and so would this, and this term, as well as this one. As a result, when we gather what's left, we simply have the following equation. And this then will allow us to find the dot product between A and B when they're written in general Cartesian form. And so here are two key equations you should commit to memory. The first one is the basic definition of what the dot product really means. And the second one says that if you want to find the dot product between any two Cartesian vectors, you simply multiply the two x components together and then add them to the multiplication of the y components and then add that to the multiplication of the z components, and you get your answer. Now let's talk about a few applications. And the very first one I'd like to speak about is finding the angle between any two Cartesian vectors. So here, for example, would be a practical application. Consider this cable and this one. We can define their directions with position vectors, and then we can find this angle that acts between the cables using the dot product. So let's go through how this would work. Consider these to be our two Cartesian vectors. Here's our key equation, isn't it? And if you are applying it, you simply would find A dot B and divide by the magnitude of AB, and then take the arc cosine to find the angle theta. In other words, you would use a formulation like this. But I wouldn't memorize this equation. I would keep this one in mind. So let me give you a simple application on how it all works. We'll consider this problem of trying to find the angle theta between this line and this one. Well, to do it, of course, we don't need to really use vector analysis. We can calculate it directly, can't we? For example, the tangent of theta is equal to the opposite side 3 divided by 4. And if you look up the arctangent of 3 over 4, you get your result of 36.9 degrees. I'd like to demonstrate how it can be done using the dot product. First, we have a position vector r1, which is going from here up to here. And then we have another vector, r2. And we use the dot product to find the angle between these two position vectors. In other words, we'll use this formulation. Now let's write r1 as a Cartesian vector. Here, I hope you see that result would equal 4i plus 3j. Now we're going to dot that with r2, 4i. We're going to set that equal to the magnitude of r1, and that's pretty straightforward, isn't it? It's 3, 4, 5 as a triangle, and so therefore this length is 5 meters. So here we'll put a 5, and we know that r2 is equal to magnitude of 4. And then we have our cosine of theta that we're looking for. So let's carry out the dot product and see what we get. We multiply 4 times 4, don't we? And we get 16. And then we have our j component here, but we don't have one on this side, so that would be 3 times 0. And of course that gives us 0. Therefore 16 plus 0 is our result of 16. We set that equal to 20 times the cosine of theta. And then, of course, finding theta means finding the arc cosine of 16 divided by 20. And when you do that, you get your answer, 36.9 degrees. But this is a very powerful method to solve a very simple problem. It really works well in 3 dimensions, as you'll see in a forthcoming lesson. The second application of the dot product is to find the projection of a vector onto a line or in a particular direction. Let me show you what I mean. Consider this conveyor belt, which is being supported by the force in the strut. If I want to find the projection of this force along the conveyor belt, what you need to do is to drop a perpendicular from this point, the end of the force, to the conveyor belt, like this. And then you can project the force along the conveyor belt. And this is our projected force. It would be as if you have a light beam back here shining on the force, and this is what you would see on the screen. Let's practice this idea then of finding projections. Consider this force, and we want to project it onto the u-axis and onto the v-axis. Do you see the projection of the force onto the u-axis? We drop our line perpendicular to the axis, and here's our projection. And what about over here on the v-axis? Do you see the projection of F onto it? It looks like this, doesn't it? Now, of course, these two vectors don't add up and give us our resultant. If we want to find that, we'd have to use the parallelogram law. For example, you go to the tip of the force, and you draw lines that are parallel to each of the axes. And then, of course, you could write in the components like this. So the parallelogram law says that these two vectors add together and give us our resultant force. And they're certainly different than the ones that we have over here. Actually, if you think about it, only when the u and the v axes are perpendicular to one another, such as an xy coordinate system, will the projection of the force onto the axes be equal to the components of the force onto the axes. But that's a special case. Let's practice the idea a little bit more so you really fully understand projections. Do you see the projection of this force onto the u-axis? It looks like this. And the projection of F along the v-axis? Like this. All right, now let's extend this idea in 3 dimensions. Would you be able to see the projection of this force F along the axis of this boom? Graphically, you would have to show a line drawn perpendicular to the axis like this, and here, of course, is our projected vector. Let's do it one more time. We want to show the projection of this force along the line OA. Do you see that? Here's our perpendicular from the tip of the force to the line, and here's our projection. Okay, now let's talk about actually finding it. Consider this vector A, and here's a line AA, and the angle that the vector makes with the line is theta. We want to find the projection of A along the line. Drop our perpendicular like this, and the projected vector we need is right here, and we'll call it A of A, the vector along the AA axis. To find its magnitude, it's simply equal to the magnitude of A times the cosine of the angle theta. But we can do it with vector analysis as well. Let's consider a unit vector that defines the direction of our axis, and we'll call that U of A. Then we can consider a dot product between U of A and A. In other words, we can write A of A, that is the magnitude of the projected vector, equaling A, the vector, dotted with U of A, the vector defining the axis, and it will give us our result right here. Why is that? Well, let's consider it. A dot U of A, the magnitude of A, times the magnitude of U of A, which is 1, times the cosine of the angle between the two vectors. In other words, our angle theta, the angle between U of A and A. So this makes a rather straightforward way in which we can find the projected vector. Just take the vector that you want to project and a unit vector in the direction in which you want to find that projection and do a dot product. Of course, you can also do it another way. You can find the angle theta between, say, vector A and U of A using the ideas we just finished talking about, that is, finding the angle between the tails of two vectors. Put that angle in here as the cosine of theta, multiply it by the magnitude of A, and you get your answer that way. But I think it's simpler to do it in this way. Therefore, we'll consider using this method. And as a simple example of how it all works, we'll consider doing this one. Here we want to project the vector r along the x-axis and express the result as a Cartesian vector. Well, again, it's a two-dimensional problem, and you really wouldn't want to use vector analysis to solve it. Basically, I think you can see what the answer is. This vector has a magnitude of 4 meters, and of course it has a direction, which is in the I direction. And so certainly the answer is simply r of x is equal to 4i. But we'll do it using vector analysis. Here's our r of x that we want to find, and here's our r vector. To solve the problem, we need to define this axis, the x-axis, because we're going to project our vector r onto the axis. So in order to get r of x, we can use our dot product. r dot I will give us our result. And now we'll work it out. R of x, in magnitude, of course, is equal to r, and r, as you know, is equal to 4i plus 3j. And we're going to dot this with I. When you carry this out, our answer comes out to simply be equal to 4. And the reason is because we take this component, the I component here, and dot it with the I component here. In other words, 4 times 1. That's why we get 4. And of course, the other component, 3, is multiplied by 0 over here. That gives us 0. So we get our result of 4. And of course, this is in meters. Now let's say that I want to express this as a Cartesian vector. Well, that's pretty straightforward. If we do that, we can write r of x as a vector, equaling its magnitude, which we found to be 4, and its direction, which is defined by our axis, in other words, I. So here's our answer in Cartesian vector form. Simply take the magnitude that you find and multiply it by the unit vector that defines the axis, and you get your result, 4i meters. Finally, let me show you what would happen if we did it another way. Let's say that instead, I define my axis going in the negative direction instead of the positive direction. You can make this go either way, either to the right or to the left. It really doesn't matter. But let me show you what happens when we consider this case. Here then, we would again find our result for r of x, and that would equal our same vector of 4i plus 3j. And now we're going to dot that with minus I. When we do this calculation, if we get our result for r of x, and it equals minus 4. And of course, this is in meters again. The negative sign tells us that we screwed up the direction in which the unit vector goes. It goes the other way, really. But anyway, realizing that, I can still get my result that I had previously. But I have to retain the negative sign here and this one as well. So in other words, as a vector, r of x is going to equal minus 4 times minus I. And if when we work this through, we get plus 4i again. The same result we had previously. There we are. And so having completed the problem, we'll end our lesson.